Hello, and welcome to this presentation, Understanding SPI. This presentation will provide you with a brief technical overview of the Serial Peripheral Interface, or SPI protocol, and how it's used to transfer digital information. SPI, also referred to as just SPI, is a 4-wire serial interface, originally developed by Motorola in the 1980s. SPI provides speed improvements over other serial data protocols, such as UART or I2C, and can also support full duplex communication. However, SPI is somewhat loosely defined in that it does not specify frame formats, number of bits transmitted, or even voltage levels. SPI is most often used for transferring data between a smart controller and a less smart peripheral device. Many applications use SPI, some of the more common being different types of sensors, displays, ADCs and DACs, real-time clocks, wired game controllers, etc. SPI is a so-called master-slave protocol with a single master and one or more slaves. The master is sometimes also called the controller, and slaves are sometimes called peripherals. Master and slave are normally connected by 4 wires, although in some special cases, not all of these 4 wires are required. The chip select wire is used to select which slave the master wants to communicate with. The synchronous clock signal is used to provide timing and synchronization. Data from the master to the slave is sent on MOSI, that is, master out, slave in, and data from the slave to the master is sent on master in, slave out, or MISO. These are the names we'll be using in this presentation, but please keep in mind that there are many other names used for describing the components in SPI-based protocol systems. Let's start with a high-level overview of SPI. The master pulls the chip select line low to indicate to the slave that data is incoming, and then starts the clock. The MOSI line is used to send bits to the slave, and if the slave has bits to send to the master, these are sent back using the MISO line. At the end of communications, CS is pulled back to high. In the remainder of this presentation, we'll discuss each of these steps and lines in much more detail, and explain both various configuration parameters, as well as how a master can communicate with multiple slaves. The first line we'll look at is CS, or chip select, which is also commonly referred to as slave select. Unlike most of the other signals in SPI, CS is typically active low, and therefore you'll often see it written with an overbar. As mentioned a few moments ago, communication with a target or slave is initiated by the master pulling the CS line low. The attached slave then listens for the clock and MOSI signals from the master. When communication is complete, CS is returned to its idle state. The greatest advantage of using chip select is that it's a very simple way to address targets. It doesn't require the kind of explicit addressing used in some other serial protocols, like I2C or CAN bus. In the case of multiple slaves, these can be addressed using either a single CS line or multiple CS lines. We'll come back to this topic later in this presentation. After the master pulls CS low to initiate communication, it then begins to generate the clock signal. One of the advantages of this arrangement is that slaves do not require their own clocks, even when they're transmitting data to the master. SPI does not have a standardized clock rate, but typical maximum speeds are in the megahertz range, which means that SPI is usually faster than other common serial data protocols such as UART or I2C. The purpose of the clock is to indicate to the receiver when data should be sampled, that is, at what time the voltage level on the data line should be read. As with most other digital data transmission schemes, 1 bit is read per clock symbol. The clock speed in SPI can either be idle at a low state or at a high state, and data can be sampled on either the rising or the falling edge of the clock signal. We'll cover this topic in much more detail later in this presentation. Once the CS line has been pulled low and the clock signal has been started, MOSI is used to send data from the master to one or more slaves. This data is usually sent in the form of 8-bit bytes, either with least or most significant bit first. The number of bytes sent is also implementation dependent. SPI can send multiple bytes sequentially over MOSI, and the protocol also allows for CS to be held low while sending multiple bytes. But like many other things in SPI, this behavior is also implementation dependent. MISO is used to send data from the slave to the master. Note that not all SPI implementations use MISO. There are many kinds of devices, such as displays, that only receive data from a master, and this is an example of where SPI may use less than 4 wires. MISO data is also commonly sent as a response to data received on MOSI, for example, queries for data, commands to set parameters, etc. Remember that in SPI, only the master generates the clock signal, so in order for a node to transmit data on MOSI, the master must know how many bits the slave wants to send, so the master can generate an appropriate number of clock cycles. This may be a fixed amount, or something that the master learns from querying the slave. Now that we've discussed the basics of SPI, there are 3 other aspects of SPI we need to go over. The first 2 are clock polarity and clock phase. As we'll see, these must be configured identically for all connected SPI nodes. The third topic is an overview of how multiple slaves can be connected to a single master. As mentioned earlier, the serial clock signal generated by the master can be either active high, in which the idle or non-clock state of the line is low, or it can be active low, where the clock is held high when no clock pulses are being sent. CPOL indicates which of these 2 is being used. CPOL 0 means active high and CPOL 1 means active low. For both types of clock polarity, we can refer to both the leading or first edge of a clock pulse and the trailing or second edge of a clock pulse. Note that for CPOL 0, the leading edge is a rising edge, and for CPOL 1, the leading edge is a falling edge. Using the terminology leading or first edge and trailing or second edge can help to avoid potential confusion or ambiguity. This will be important for our next topic, clock phase. In SPI, a receiver may sample the MOSI or MISO data on either the leading edge or the trailing edge of the clock signal, and this is referred to as the clock phase. There are 2 possible clock phases. Clock phase 0 means that data is sampled on the leading or first edge of each clock pulse. Clock phase 1 means that data is sampled on the trailing or second edge of each clock pulse. In both of the examples here, the clock signal has polarity 0, that is, the clock is idle low. 2 types of clock polarity and 2 types of clock phase yields 4 possible combinations. These parameters are often summarized as a single number, 0 through 3, which is called the SPI mode. As you might imagine, all interconnected SPI devices must be using the same mode. Mode may either be fixed in hardware or be user configurable, depending on implementation. Note that the mode can often be determined by inspecting the SPI waveforms. For example, here we can see that this clock signal idles high, so clock polarity equals 1. We can also see that data is, hopefully, being read on the trailing edge of each clock pulse, so clock phase also equals 1. Therefore, SPI mode 3 is being used for this communication. Of these 4 modes, mode 0 is, by far, the most common mode used in SPI implementations. The last topic we'll touch on is multi-slave configurations. One way a master can communicate with multiple slaves is by having a separate CS line for each slave. To address a slave, the master pulls that slave's CS line low. All other wires, that is clock, MOSI, and MISO, are all shared between the nodes. This configuration is often referred to as independent slaves. Although this method is relatively straightforward, there can be issues scaling this above more than a few slaves due to the need to have a separate CS line for each slave. The other common multi-slave configuration is called cooperative slaves, or a daisy chain configuration. Here, the master has only a single CS line which is shared among all slaves. And, as with independent slaves, the clock signal is also shared among all slaves. However, in this configuration, MOSI data is sent to the first slave, and then additional clock cycles can be used to pass it along to the next slave in the chain. This is done by connecting the first slave's MISO to the second slave's MOSI. This process can then be repeated to pass data to the next slave. If the first slave wants to send data to the master via its MISO line, this data is routed in the same way from slave to slave until it reaches the last slave, whose MISO line is connected to the master's MISO. Although cooperative mode reduces the number of required CS lines, it is more complicated and may not be supported by some SPI devices. Let's end with a brief summary. The Serial Peripheral Interface Protocol, abbreviated SPI or SPI, is a very common 4-wire interface used to transfer information between a controller or master and one or more peripheral devices or slaves. These 4 wires are chip select, serial clock, master out slave in, and master in slave out. The CS line is used for addressing, and MOSI and MISO are used to transfer data from and to the master. The SPI clock signal can be either idle low or idle high, and data can be sampled on either the leading edge or trailing edge of clock pulses. The clock polarity and clock phase must, however, be the same for all nodes. These parameters are usually summarized in the form of a mode number. And finally, multiple slaves can be connected to a single master, either independently, that is, with separate CS lines for each slave, or in a cooperative daisy chain arrangement. This concludes our presentation, Understanding SPI. If you'd like to learn more about serial data protocols or how to decode serial data using an oscilloscope, please see the links in the video description. Thanks for watching.